welcome to today's lecture. Last time we looked at the simplex algorithm to solve linear real arithmetic formulas, and today we recall again the SMT approach, SAS modulo series approach, and look how simplex can be embedded into this approach. So this problem we already know. The stated formula is the Christmas problem as a Boolean combination of constraints, linear constraints, and actually the variables were real values, but integer values, but we assumed for the first that they are real. And then we got known to this SMT approach, which combines a SAS solver and a series solver, whereas now here in the series solver we instantiate this with the simplex algorithm. So let us look again at the example how it works. This is our constraint. We already looked at how SMT works. So from this formula, which contains constraints from linear real arithmetic, we first make a Boolean abstraction. And this is the one at the bottom. And first we search for Boolean solutions for this reduced problem, for this abstraction here. And if we find a solution, then we check if the corresponding constraints which are abstracted by the Boolean variables together are satisfiable or not. So now from the SAS solver, we first try to get a solution for the Boolean abstraction. This we already looked at, so we have this Boolean formula and search for a satisfying solution, and we find one, and this is given by the assignment, given here at the top. And now for those variables which are true, we collect the constraints. And this gives this constraint set at the bottom. And now we use simplex to check if this set of constraints together is satisfiable. So how does it work? On the left here we have the set of constraints whose Boolean abstraction variable is true. Now first, as we have seen, we have to bring it to general form, to the form AX equals B with some bounds on the new fresh slack variable. So if you look, for example, for the first constraint, P1 plus P2 plus P3 larger equal 100, then we take a new variable S1, which encodes the value of the left-hand side, so P1 plus P2 plus P3, and we just put a bound on its value. So it is equivalent, but instead of a set of inequations, we have a set of equations and a set of bounds. And we do this similarly for the other constraints also. And now you can see here, we have, instead of this form, the matrix just contains this part for P1, P2, and P3, just the coefficients. This is given here. This is the initial tableau for simplex, and we start with an initial value 0 for each variable. Okay, if you look how it can be solved. I just write. Oh, I'm sorry, I forgot something. Firstly, if you are in bachelor and want to make the exam for master, then after new regulation, you have to register at ZPA. So it is not done by Science anymore, but you have to register, and the dates where you can register are the 10th till the 21st of December. Then I also wanted to convince you to visit the Tag der Informatik, Day of Computer Science. It is on the 7th of December in the afternoon. You also already see the announcements on the floors. And the last thing is to the exam. We fixed 2 dates, and to decide which 2 dates these were, we try to collect the dates of all exams and try to find the sorts that there are no exams. But I think there was one which in the first semester, numeric, something like this, and there was another exam which is on the same day, but not at the same time. So it is still possible to do the exam for this lecture without missing another exam. It is really very hard to find time point where everybody can come. Our offer, if you cannot come to the first exam, then you can, we will try to arrange that you can register just for the second exam, such that you do not fail for the first if it collides with some other exams. So if you have some problems which you cannot solve this way, then just come to us and we will try to find a solution. And after the second exam, we will offer appointments for oral exams. So for example, if you have 2 times, I don't assume that 2 times you do not manage to make the exam, but in case you do, then you can have further exams at the end of this semester or at the beginning of the next semester. Do you have any questions to this organizational stuff? Yes? Please? I think the exercise sheet will be in English, but if in the exam you want to write German, that is no problem. But only the languages English and German are allowed. So if there are no more questions, then I'm sorry for the interruption. This was our problem. Here's our tableau, initial tableau, and we want to solve this problem now. So I just write it here down again. The first problem is we have 6 inequations and 3 original variables, and the tableau looks like this. So, and the original assignment is all variables are 0. What do we have to do before we start solving? We have to fix something in order to terminate. And this is the variable order. So let us take S1 is the first one, then S2, S6, and then the P's. Okay, this is the variable order static. Do not change during solution. So what is the first thing now that we do? We have the initial assignment. Does it fit? Oh, I missed the constraints. Sorry. S1 is larger or equal 100. S2 is larger or equal 10. S3 is less or equal 180. This was the time. These were the costs. Okay, and these are the bounds. So I have now an initial solution. Everything is 0. Is it a real solution to my problem? No, because? Exactly. But now we first check in this tableau. We have the initial, the invariant that P1, P2, P3 satisfy the bounds, but the SI doesn't have to do. And now we have a variable order. We search for the first one in this variable order which violates its bound, and this is S1, because the value of S1 is 0, but it should be at least 100. So what we do is that we pivot and pull the value of S1 to 100. How do we do this? If I look, what is this line? What does this line state for? Is S1 is P1 plus P2 plus P3. And now I want to pivot. Sorry, I take P1. This is suitable because the coefficient is not 0 and P1 doesn't have any bounds. So I will pivot them. I will exchange them. So I need an equation P1 equals something, and this is S1 minus P2 minus P3. So I change the tableau. Now here I will have P1 and here I will have S1. The rest is the same. And now the first constraint changes from this one to this one. So the coefficients will be 1, minus 1, minus 1. And in the remaining rows, I will take the values from the first tableau. But for example, if here I have a value, then I will replace this coefficient times now the right-hand side of the equation. Because now I don't have P1 there anymore, but S1. So S2, the second line is independent of P1. So it will remain the same. S2 is still P3. But now in the third row, S3 equals P1 plus 2P2 plus 5P3. And now I need in the next tableau, P1 is not in the column anymore, but in the row. So now instead of, I have to express it by S1. So actually it is, I take this equation here, S1 minus P2 minus P3 plus the rest. So what I do is I take this column, and instead of the 1, I take 1 times this first row. So what I get is 1, then 2 minus 1 is 1, 5 minus 1 is 4. And I do this for all rows. So now I do it algorithmically, just showing what is the meaning. Of course, if you do this automated, then you have some rules. Just the same, but formulated in just going over the indices and changing everything. So what is for the fourth row? S4 is 3 times P1, so I will have to add 3 times the first row. And this is 3. Then here I have a 2 minus 3 times minus 1 is minus 1. And 1 minus 3 times minus 1 is minus 2. And I do this for the remaining rows are not affected because the coefficients for P1 were 0. So it is not changed. Okay, what I did now is just a reformulation of the equation system. I just changed the variables S1 and P1 by pivoting, and now I also have to adapt my valuation, the assignments to the variables. So firstly, S1, now we go for the columns. S1 is the one which we wanted to pull into its bounds. So I give it the value 100. The other column variables do not change. So alpha of P1 remains 0, P2 remains 0, and also P3 remains 0. Now to the lines. The first line can be just computed now from the values of the S1, P2, and P3. So P1 is 2 times S1 with the value 100. The rest is 0, so it is 100. For the second line, P3 is 0, so the second S2 is also 0. The third line is just 1 times S1, because the other is 0, so 100. The fourth line for S4 is 300. The S5 is 0, and the S6 also 0. So we finish now one pivoting. And now we will check again. Are the bounds satisfied? Now we go in the order. S1 is now on the top, so it satisfies its bound automatically. S2 is larger or equal to 10, but its current value is 0. So we have to pivot again. I just remove these lines. So we want S2. Which variable is suited for pivoting? It is trivial. P3, because all the others do not play any role in this equation. I have S2 equals P3, so if I modify S2, then I have to modify P3, otherwise the equation doesn't hold. P3 doesn't have any bound, and note that if I pivot them, I change them. Since it is an equation S2 equals P3, by reformulating the equations, I get P3 equals S2. So on the tableau, nothing changes but changing the variables. The coefficients do not change. But the assignment changes. So the new valuation is S1 is still 100. P2 is still 0. But now S2 is pulled to its lower bound 10. And I go for the rows. What is P1? 1 times S1 minus S2, so it is 90. P3 is just S2, it is 10. S3 is 1 times S1 plus 4 times S2, so 140. S4 is 3 times S1 minus 2 times S2, so it is 280. For S5 we have just 10, and for S6 we have 0. So we check again. What is about the bounds? Here S3 should be at least 100, at most 180, and it is currently 140, so it fits. S4 should be not more than 300, but it is 280, so it fits also. S5 should be 0, but it is currently 10. So S5 is outside the bounds, and the only variable which is suited for pivoting would be S2. S5, the value of S5 is too high, so I should make it smaller. However, S2 is 10 and it is on its lower bound, so it is not suited for pivoting. That means I have a conflict here. The problem is not satisfiable. And now the corresponding inequations, which are unsatisfiable, I can read from reading the select variables of the row, which cause the conflict, and the select variables of all columns whose coefficient is not 0. That means S2. These correspond to two constraints, which together are unsatisfiable. I go back one slide, and we see the second line is for S2 is P3 larger or equal 10, and the 2 and 5. 2 and 5 sorry, I think I missed the Pivot 2, and this is right. 5, and I think I have a this would be 2 and this would be 5. Ah. Ah. So I had, sorry, but this is the same as here. So as 111, 001, 125. Ah, I solved the next problem. You see, this is my mistake. The one was in the middle. May I go back short to check if this was? No. Okay, I know what the problem is. I was right what I wrote down, but this belongs to this. So my only problem was that somehow, instead of going back, I went forward, and I wrote it after the next problem. But this is the tableau for the first invocation. So it was 2 and 5. And if we take 2 and 5 here, then we get the right constraint. And that means that P3 equals 0 and P3 is larger or equal to 10 together are unsatisfiable. This is the answer of the theory solver. And if we look here at this picture, what we did is we called the theory solver with a set of constraints, and now we come back with an explanation. Now we add a new clause explaining this conflict. That means we add some additional information that was not available before in the Boolean domain, and that's why we call it abstraction refinement. So we put more and more information into the Boolean formula until it is so precise that we can decide its satisfiability in the pure Boolean domain. What would happen if our solver could not give us a subset of these constraints, if it would just say unsatisfiable? Why is it better to have this conflict clause added?
Conflict clause, we won't run into the same conflict.
Exactly. So if the solver would have just said the set of constraints is unsatisfiable, this set, then the subsolver could not do anything else than excluding this combination. But perhaps just removing one constraint and adding another one, but still keeping the two conflicting ones, could still happen. So the smaller the answer, this unsatisfiable set, the better it is for the sub-search, because the more information we lift from the theory to the Boolean domain. So it is unsatisfiable, and we added this new clause, and we continue the search. What happens now? We had here the conflicting assignment at here and here. So now what the subsolver will do, will undo these assignments, because now with this new information, it can already imply at decision level 0 from the value of A7 being true, that not A7 is false. That means this clause is unit and can imply something new. So we backtrack, put this information there, and continue the search. And here you can see the result of a new search. And now we again take all Boolean variables whose value is true, collect these constraints, and put a new check. These are these constraints here, which are true, and ask again the theory solver if these together are true. Okay. So now it is indeed the one that we have to check, and we do the second check. Again, what do we have? We have still 6 constraints, and we have still 3, P2 and P3, still 3 problem variables. So the differences in S5 and S6. We have the same initial and the bounds are similar. S1 is larger or equal to 100, S2 is larger or equal to 10, S3 is less or equal to 180, S4 less or equal to 300, and S5 is 0, and S6 is larger or equal to 5. Okay, we take the same ordering S1 is the smallest and P3 is the largest. So we start again. S1 has the value 0, but it should be at least 100. So again, we have to pivot. And the first one that is suitable in the order is P1. So again, I flip from S1 equals P1 plus P2 plus P3. This is the equation encoded by the first line. And since I want to pivot them, I need something that P1 equals, and this is S1 minus P2 minus P3. Minus P2 minus P3. So what I have is this equation here will be encoded in the first line. And now for the other lines, again, I replace the coefficient for P1 by the coefficient times the first row. So for S2, nothing changes because it was independent of P1. For S3, I have the first row plus 1 times the third row. So 1, 3, sorry, S3 is P1 plus P2 plus P3, 1 minus 1 minus 1. Yeah, so I have here 1, 1, 4. Then for S4, I have 3 times the first row. So 3, 2 minus 3 times 1 is minus 1. And 1 minus 3 times 1 is minus 2. And S4 and 5 are independent of P1, so they remain the same. Okay, this is the new tableau. And we also need to compute the new assignment. S1 is pulled to its bound 100, from 0 to 100. And P2 and P3 are unchanged, so the value is 0. We must not change the values of the other variables, P2 and P3, because otherwise we could violate the invariance that they remain in the bounds. So we only change the rows. P1 is now, I can compute its value. It is 100 because it is 1 times S1. P2 and P3 are 0. The value of S2 is 0. The value of S3 is 100. The value of S4 is 300. The value of S5 is 0, and also of X6 is 0. So I'm done with the first pivoting. Then we check again. P1 doesn't have any bounds. S2, the value is 0, and it should be at least 10. So we should pivot for this. The only variable that is suitable is P3, because the remaining coefficients are 0. P3 is also suited because it is the original variable, doesn't have any bounds. And it is similar as before. From S2 equals P3, we get P3 equals S2, so the tableau itself doesn't change. I only exchange the variables. Nothing else is modified, but I also update now the assignment. The value of S1 doesn't change, and of P2 also not, but now I have S2 pulled into its bounds. So S1 is still 100, P2 is still 0, but now S2 has the value 10. And I recompute the rows. P1 is 90, P3 is 10. The row for S3 gives us 140. For S4, we have 280. for S5, 0, and for S6 also 0. Okay, are we done? Is it a solution? S6 is too small. Its current value is 0, but it should be larger, equal 5. Is there any variable suited for pivoting? P2, it is an original, so it doesn't have any bounds. I can take it. And we have luck. The coefficient is 1. That means I can pivot them again, and the coefficients do not change. I only have to update the variable values. So here I have S6, and here I have P2. And I update the values. So S1 remains 100, S2 remains also 10. What changes here is the value of S6 is now at the bound 5. Okay, we recompute the rows. P1 is now 100 minus 15. This is 85. P3 is 1 time S2. This is tier 10. S3 is now 100 plus 5 plus 40. S4 is 5 less. S5 is now 5. And S6 is also 5. So we are done with this pivoting step. Is this a solution? No, we just shifted the problem from S6 to S5, which now has the value 5, but it should be 0. So S5 should be pivoted. The only variable which could be suitable for pivoting is S6, because this is the only variable with coefficient not 0. But S5 is too large, so I should reduce its value. The coefficient is positive. That means I should reduce the value of S6, but S6 is already at its lower bound, so it is not suited for pivoting. That means we have found out that this problem is also unsatisfiable, and the constraints which are together unsatisfiable are S5 and S6. Here. Yeah. And S5, I'm sorry, there is the problem encoding. Here, 5 and 6. Now these were the two constraints. So the conflict that is given back is these two, and the abstraction of these two are A2 and A6. So now I do the same as before. In the SAT solver, I got a problem, and now the theory solver simply gives back an explanation, and this is used to refine the Boolean abstraction by a new piece of information that A2 and A6 cannot hold together. So again, conflict resolution is done. This we already discussed last time, and the solver searches for a new solution. Now it has found one, and we do the same thing. The abstraction of the theory constraints for the true Boolean variables should be put to the theory solver, and these are, the red ones are again a true constraints, and this is the encoding. We go again. Here, first the problem is formulated into general form, and we have here the tableau with which we start. The initial tableau, I just write here again. And now we are nearly done with the check. Okay. The constraints, the bounds on the and initially everything is 0 again. Okay. We check. We start with the same problem, namely that S1 is outside its bound, so we have to pull it up to 100. That means S1 must be pivoted, and P1 is the first in the variable order which is suited for pivoting. So the same as before, P3. From this I can imply that P1 equals S1 minus P2 minus P3. So I can pivot the two, and I get the following tableau. One minus 1 minus 1. The next row for S2 was independent of P1, so it remains the same. For S3, I have basically these two components plus 1 times the first row, this one. So what I have is 1, 2 minus 1 is 1, and 5 minus 1 is 4. For S3, I have to take 3 times the row for P1. So I have 3, 2 minus 3 is minus 1, and 1 minus 3 is minus 2. And the S5 is independent, linear independent, so it does not change. And S6 is P1, so I just take the first row. I have to recompute the assignments. So S1 is now on its bound, and P2 and P3 remain 0. Now for the rows, P1 is 100, S2 is 0, S3 is 100, S4 is 300, S5 is 0, and S6 is 100. Okay, we are done with the pivoting step, and check again. P1 is an original variable. S2 has the value 0, but it should be larger or equal 10, so we have to pivot. Again, there is only one variable which is suited for pivoting. This is P3. And this is this lucky case where the coefficient is 1, so I can exchange them without changing the tableau. So S2, P3. And I just have to recompute the values. Now the value of S2 is 10. I've pulled it to its bound. And we have to recompute the rest. P1 is 90. P3 is 10. S3 is 140. S3 is 280. S5 remains 0, and S6 is 10 less, so 90. Okay, we check again. P1, P3 are without bound. S3 is at most 180, but it is 140, so it's 5. Fine. S4 should be not more than 300, but it's 280. S5 should be 0, it is 0, and S6 should be larger, equal 5, and it is 90. So it fits. That means we have found a solution, and we can give back to the SAT solver the solution is also consistent in the theory, So we have found a satisfying solution how to make the presence. What we did not discuss now is incrementality. I told you last time, as we were discussing this SMT approach, that now in this example, first the Boolean solver search, the SAT solver searched for a complete solution, and then sent all the constraints in one step to the series solver. Now, if you have big problems, then it can be disadvantageous to let the SAT solver work so long, because perhaps already at the beginning there were some conflicts in the series. So it would be perhaps better to just make some decision levels and then before continuing ask the series solver if the current combination of series constraints is still satisfiable in the series domain. This is called less lazy SMT solving. And in this case, I just go back to our problem. Here, for example, if I am ready with decision level 0, then we would ask the series solver, are A4, 7, 8, and 9, the constraints for them, satisfiable together? And in this case, I guess the solver would say yes. Then the SAT solver would come back and make a new decision level. And it would assign A2 and A5 also true. So now the series solver should check 4, 7, 8, 9 plus 2 and 5 together. And if it starts from the very beginning of the check, then it just redo work which was already done before. So it was better if we would have something incremental that the solver could use the first check, the state of the check which was there satisfiable, and extend it to add some more constraints. How could it work in simplex? Do you have any idea? So I have now, I go back to the beginning, to the abstraction. Here I have this formula, I have the Boolean abstraction, and here I have a set of constraints, 9 constraints. And I assign some of them true and send it to the series solver, to the simplex solver. And afterwards, I would like to assign some more constraints true, and I would like that simplex somehow makes use of the previous check. Do you have any idea how we could reuse the result of the check? If it was satisfiable. If it was unsatisfiable, then we anyhow have to backtrack. But assume a set of constraints was satisfiable, and then I get, let's say, one new constraint.
We can add a new constraint, and we can use the solution from the last series check, and just go from the old solution and do a new iteration.
Yeah, this is already a good idea. There is one problem. I think I will go to the end of the slides. Incrementality. There is one problem. Assume we had a tableau initially. I had here P1 to Pn and S1 to Sm. And then we checked, and I got here some, let's say S1, just an example. This is the tableau after the first check, and this is satisfiable. And now I get a constraint, let's say P1 equals 0. What would it do? P1 or M plus 1 equals P1, and Sm plus 1 equals 0 is the bound. Now I would like to add this row, but if I add here Sm plus 1, which should be the coefficients here? this could be done. So we could transform also those rows, but we actually do not consider them in the bounds. We say that we do not activate the bounds. We consider them as variables without bounds. So if I have this Sn+1 constraint, n+1 constraint, you see here the problem is that now I do not have P1 here, so I cannot express my constraints so easily. But nevertheless, I could take the row of P1 and add it in here. This way I would kind of replay the pivoting for the new constraint. But it can be expensive, so what is indeed done in praxis is that I take here n+1 already, the constraint, I add it even if it is not active. And then if it gets active, then I just add the new bound on Sn+1. So in our example, I had how many? 9 constraints. So I would create a tableau with 9 rows. And then if I get 6 constraints, then I activate the bounds on these 6 constraints, and I update the tableau, search for a solution. And if it is satisfiable and I get a new constraint, the 7th, then I activate the bound on the 7th. And if now my tableau does not fit, then I just continue pivoting. This way it is truly incremental, so you do not have much overhead, but you have to update also those rows. And this can also be optimized in that we update them only partially. So you can have some flags which tells you that these rows are not up to date, so if you need them, then you will have to make some computation. This is incrementality. I did not make it in the example because the tableaus were large enough to write, but this is done in praxis. The minimal if feasible sets we already have looked at. What we also did not do is backtracking. So if you found out that the theory has a conflict for the current constraint, then the SAT solver backtracked, and in the series solver next time we started from scratch, from new. This can also be changed, so we could remember the history of pivoting. And if you find a conflict, then we could just basically undo some of the pivotings, but we can also let the tableau as it is. If it was satisfiable, then by undoing something, it will remain satisfiable. So backtracking is not a big problem in simplex, but in praxis, it is often cheaper to start from the beginning because you have a solution. So the tableau you can actually keep, but your solution, if you have afterwards new constraints, then it is sometimes better to start at 0 again, because then you reach a corner, a vertex faster. But it is also complete if you start from the last solution. Perhaps some more words to optimization. What happens if I have 2 constraints? If I bring it by the original method to the equation form, then I have this. So I have a 2 times 2 matrix. Can I optimize something in this case? Can I do something more efficient? Exactly. They encode the same term. So I can search for equal terms in my theory constraints, and then I can try to reduce the number of auxiliary variables, of these slack variables. So instead of S1 and S2, I can just take one, and I can put 2 bounds on it. So here I use also S1 to encode it. I could, if it helps, even if I have, let's say, x plus y equals 0, and x plus y plus z is larger or equal to. Once I encode it here, x plus y equals S1, I can also use S1 here. But we have to take care that afterwards we have still enough slack variables such that in the tableau that we generate, initially the invariance, so the bounds must hold for these variables, only for these variables not. So the matrix size should be at least such that I can formulate it in a way that the invariants hold. Okay, some further pre-processing techniques we will look at later, but these are the basic ideas. Good. Do you have any questions now to the simplex application? Okay. Then we have seen in this Christmas problem that we had integer valued variables. So we applied simplex to solve this problem, but it could have been that simplex gives us a solution which is not integer valued. And then we cannot make use of it because half a present is not something you would like to have. So in this case, we need methods for linear integer arithmetic. Also, this logic is decidable, and why we have a look at it now is because you can use the simplex method and extend it to solve integer problems. And the idea is very simple. So let us have a look at it. This is called branch and bound, and during I explain, we will recognize why it is called this way. First, some definitions. If we have an inequation system, or formulated in the general form, it's an equation system. This is like before. And notice that we can have now lower and upper bounds. And this is due to the fact of the simplification, that one term can encode, appear in different inequations, and then I can use the same slack variable for encoding. And now it is an integer linear system. If we have, additionally to the previous problem, the integrality requirement, that means that all variables are of type integer. And once we have an integer linear system, I can come back to the real valued problem by a relaxation. That means I allow not only integer values, but also real values. So, assume we have now 3 inequations, and since the inequations are all linear, they define a polyeder, or if it is closed, then a polytope. So the green area is the solution for this set of inequations. And now the integrality requirement puts a grid on it. That means I do not want to have an arbitrary solution, but an integer valued solution. And now if we look at how simplex works, basically it always searches for vertices of the problem. In the initial case, sometimes it finds some value also on the edges, but mostly it will find, also later in the optimization, find vertices. So assume now the blue one is the found solution that simplex gives us. And the problem is that it is not integer valued. It is not quite clear for the x-axis, but for the y-axis we can see that it is not an integer value. So what to do now? Can I use simplex somehow to force him to search now for another value which is integer, or at least to exclude this value and tell him, give me a new solution? So simplex has found the blue solution, and I would like to exclude it. How can I exclude this solution from the solution space? And actually what I would like to have is to exclude not only this single point. If I would exclude this single point, that I would get an open set. And what would be better is to exclude a subset of this green one without excluding any integer solutions, but to exclude some real valued solutions which are not integer.
Maybe I can insert a branch which, a new equation which inserts the condition that I will land on an integer value. For example, here I could say y greater or equal to. So I cut off the small triangle below.
Yeah? So we have here a blue value which is not real. And I search for one dimension in which the solution is not real valued. And I know that everything here in between are real valued solutions in the y dimension, and there are no integer solutions in it. So there are integer points in the x dimension, but not in the y. So this whole set here I can exclude. I can also do it in the other dimension if you assume that this solution here is also non-integer. But now we have chosen this. So we can say in the future search only for solutions whose y value is either less than 1 or larger than 2. Less or equal 1 or larger or equal 2. But in between, it is not, there is no solution. So what we have now is that we branch the search. We made a branch on the search. That's why it is called branch and bound, in that we search either in one of the half spaces or in another one. So what would happen if we continue now? Let's say we check the lower part. It will be found out very fast that it is unsatisfiable. This one here. And if it is unsatisfiable, then we have a bound. That's why branch and bound. So we had a search, and then we tried first here. This was, we branched, tried first here, so we can bound the search, and the remaining part is the green one. So this one here is excluded now from the search. We reduced the solution space. And we continue. Now we can call simplex again. Let's say we get that point, and it can be that now it is in y dimension an integer, but in x dimension not. So we do the same. We say either the largest integer below, and I search from that to the left, or the smallest integer above, and I search from that to the right. So we branch again. Let's say we try now the right half, and if we call simplex, now we have here this blue point, which is a vertex and which is integer. So by cutting, I can have luck and find now also integer values, and then the search can stop. Okay, let us try to formalize it as an algorithm. An input is an integer linear system S, and an output is the answer to the satisfiability question. So it gives us SAT if S has an integer solution and unsat otherwise. What I do first is I relax the problem. I make from the integer valued problem a real valued problem, and I call simplex. If simplex tells me answered, then I know that it is answered, because if there are no real valued solutions, then of course there are also no integer valued solutions. The more complex case is if simplex tells us that there is a solution, then if this solution is integer, then I'm also done. And if it is not an integer, then I select one dimension where the current assignment value is not an integer, and I split, I branch. I add the constraint that now I search first for the left half space, which is below the largest integer below the current value, and if I find there a solution, then it is okay. If there is no solution, then I bound and search the other half space. If there is a solution, then I am also done. And if there are no solutions in both half spaces, then the problem is proven to be unsatisfiable. Okay. One question. The correctness of this algorithm is easy to see. What is about completeness? Is this logic decidable? The integers with addition? Linear arithmetic over the integers. Is this logic decidable? That means, can I get an algorithm that for all formulas from this logic can give me the answer of if the formulas are satisfiable or not? Yeah, this is decidable. But if you add multiplication, then it becomes undecidable. So this is decidable. So basically there exists an algorithm that terminates for all inputs. For all inputs, it gives you first the correct answer. This was soundness of algorithm. And completeness means that for each input, it terminates in finite time, after a finite number of computation steps. So soundness is easy to see. Have we just looked at the algorithm and have seen that it is correct? If this gives us an answer, answered or set, then this is really the satisfiability answer to the satisfiability question. But does it always terminate? And there is one point, we have a recursive call. Yeah, the blue ones. I call the algorithm again. So can it happen that I call it again and again and again?
Because I always, in every call, I look at the subset of my solution space where the current solution is in, and with every branching, I make it smaller because I take out the area between the two integers. So it gets smaller, and it gets pretty smaller. So
at least, so the getting smaller cannot be epsilon. So it is always at least.
it has at least a size of 1.
Exactly. And your argumentation would be correct if we would have a bounded state space.
We have a finite set of variables, and we always, with every iteration, we eliminate one variable and find a non-integer value. So at one point there won't be any variables left that has a non-integer value assigned.
The problem is we do not eliminate it, we add a new constraint about it.
Yes, but that results in getting assigned a non-integer value.
No, not always. So it does not always terminate. Can you imagine one situation, one scenario where it does not, where you cut and it never ends?
Yeah, if you have a
Mm-hmm.
Like this, and you always add the friction for the first variable, and it always gets higher and higher.
Yeah.
And you are not bounded.
Exactly. One typical example is if you have a satisfiable problem, then you never know how simplex. It depends on your variable order. So it is much easier to take an unsatisfiable problem for the integers, but satisfiable for the reals. Then you know that it will never terminate with that. Yeah? But if it is unbounded, it will also never terminate with ansatz. So how does it look like? Again, this is the constraint is I have it here. So if I reformulate it, just to visualize it graphically, I try to so x minus 1/3 is something like this. Yeah, the last line doesn't fit, we just remove it. And minus 2/3 is something like this. Yeah, roundabout. So the solution space is here in between. And now we can easily see that this constraint doesn't have an integer valued solution. Why? Can you give an argumentation why this one is unsatisfiable? Yeah, but you cannot see it. Or a proof. Prove me that there are no integer solutions for this inequation.
Well, 3x minus 3y is always a multiple of 3, but 1 and 2 are no multiples of 3, and between them there is also no.
Exactly. So to see it better, we just divide by 3, and it is said that 1/3 is less or equal x minus y is less or equal to 2/3. That means the difference between the two is a fraction, and it cannot be if they are integer. So there is no integer solution, definitely. But what would simplex do? Simplex would search for a solution and find something somewhere and cut. Then search, let's say, in the right half. Would find something here and would cut again. Then search again to the right of it. Would find again some solution somewhere and cut and cut and cut and cut. And it would never end cutting because there is still an infinitely large real solution set, but there are no integer solutions, so it cannot terminate. That means that this algorithm gives us an incomplete method for something which is actually sideways. This is not optimal. But in practice it works good. So if it gives us an answer, then we are happy because this answer is correct. But if it does not give us an answer, then we need some other methods which always terminate. And this is the omega test, which we will discuss on Thursday.